Hi, it's Mr. Benson here, just making a short video on electrolysis. So just trying to clarify the ideas that we started going over in class. So as we know, electrolysis is the opposite of galvanic cells. So whereas in a galvanic cell, the chemical reactions are generating electric potential and they're moving or pushing the electrons in the external circuit. In an electrolytic cell, the direction of current is driven by the external source of power, or EMF, electric potential, and so this effectively reverses the current in the cell. With electrolytic cells, often the electrodes are in the same container, so we don't have the two half cells that we have in galvanic cells, although sometimes you will get this if you want to capture two different products and separate them from each other. So what electrolytic cells look like, very much the same, but we've just got to think about what's going on in the cell. Now, it's possible to have electrolytic cells where we are electrolyzing molten salts. So we might have something like sodium chloride and it's heated up until it's a liquid. Now we know that sodium chloride is obviously an ionic substance, and so it is Na plus and Cl minus. And they are in a liquid form, free to move around, and so a liquid salt will conduct electricity. Okay, so we've got to think about what's going on with our battery here. Now when you see the symbol for a cell like this, what it means is that this is the part that has the positive potential and this has the negative potential. Now the conventional current, which is the way people doing physics think about current, would be moving around this way, so be moving anti-clockwise, but the electrons actually go the other way, so they would be effectively flowing this direction, and we know that they're not just flowing straight through the battery because or the power supply, because there is stuff going on in there, but we're not worried about that. The only thing we need to worry about is the direction of the electron flow. So what we have is these two reactions going on, and we've got to think about where they're going to happen. So let's think about the directions that the electrons are going. There might be some other things that we can think about of as well. For example, you might recall that in a galvanic cell the cathode is the positive terminal and the anode is the negative terminal, and in an electrolytic cell that is reversed. So this is the cathode. The cathode is where reduction happens. This is the anode, and this is where oxidation happens. So we've got the cathode, the red cat, and the an anox. Good way to remember those. Now you can also think about it purely in terms of the electrons flow. Electrons are flowing down to your right and down into here, which means this is where electrons are going to be added to something in the reaction. Now the only thing that they can be added to is to the sodium. So we've got Na plus plus an electron is going to give us sodium metal. Then when we go over to the other side, obviously the opposite thing is going to happen. We've got chlorine or chloride ions, sorry, they want to, well, they don't particularly want to, but when they are being oxidized, they are going to lose 2 electrons, and we're going to end up with chlorine gas. Gas, not E. Now, have I forgotten to say anything? I don't think so. Now, as you can see, that's pretty simple when there's just 2 substances present, because one will be oxidized and one will be reduced. It gets more interesting when we're thinking about multiple species. So, let's think about a mixture of sodium chloride and potassium bromide, which is not inconceivable that we might mix these salts and melt them and then electrolyze them. So what I'm going to do, I'm going to write first the metal ions together and the halide ions down here together, and we're going to think about what's going to happen to these. Now we know that these two can be reduced, so the reaction that would need to happen to these two would be reduction. Now, these two can't be reduced further, so the only reaction that can happen to these is oxidation. Now, one thing that's worth remembering here, because it ties in with the way that the book talks about this process, is to remember that something that undergoes reduction is acting as, an oxidant, so an oxidizing agent. Something that is undergoing oxidation is acting as a reductant, is acting as a reducing agent. Now, that helps to think about things the way the book thinks about them. I think there are several good ways of understanding this other than the terminology that they tend to use in the textbooks. So, let's write in purple because it looks pretty. Let's think about the reactions that are going to go on here. We know that sodium, sodium would be gaining an electron and becoming solid sodium. Potassium would be gaining an electron and becoming potassium, probably molten potassium, but anyway. With the reactions down here, now the opposite things are going to be happening here, but what we want to think about is the reduction reactions. So these are both reduction reactions, but I want to think about the reactions that are occurring and where they sit on the electrochemical series. So chlorine wants to, so the reduction reaction there is gaining 2 electrons and giving us 2 chloride ions. Bromine is much the same, Br2 plus 2E minus gives us 2 bromide ions. I'm being a bit slack here and not writing states in because it's not important. Also, in some of these examples you'll come across, it's actually pretty cryptic as to what state things are in. Because if you think about it, when we're talking about molten sodium, the positive and negative ions are dissociated from, well, they are not dissociated, that's not the right word, they are free to move. They're not kind of bound into that rigid ionic structure, but they're definitely not aqueous. So it's a funny situation. I digress. Going on to the important bit, let's think about the reduction potentials of these ones. So we know that sodium and potassium are going to be way down in the series. So sodium we know is a reactive metal. It generally wants to be oxidized, so it has a very negative reduction potential, minus 2.71. Potassium, now if you remember, is actually even more reactive than sodium, so it has an even lower reduction potential. Now, I'm going to not continue on and talk about these ones for a sec, because we can now figure something out, and there's two ways of thinking about this. The terminology that they tend to use in the textbooks is to say, of the species that are present, choose the strongest oxidant. Now, when you have a look down here at these two, we know that these would need to undergo oxidation, so they are going to be acting as reductants. So we can ignore those from the question we're answering up here. When we look at these two substances, sodium is higher up the electrochemical series than potassium is. Now, at the top of the electrochemical series, you find substances like the halogens, like fluorine and chlorine. We know they are strong oxidizing agents. So the higher up the electrochemical series you go, are the stronger oxidants. So of these two, sodium would be the stronger oxidant. Now that allows us to go, okay, the substance that would be reduced would be sodium. I'm going to draw a very wobbly line around that. The other way of thinking about it, though, is just to think about what we know about these two substances. I find it a little bit troubling, I suppose, or annoying, it's probably a better word, to talk about this substance as being a stronger oxidant, because it's not. It's a crappy oxidant. These are, you know, the least oxidizing substances, or some of the least oxidizing substances of all. So, I suppose the way I like to think about it is, which of these has the least resistance to being oxidized, because to being reduced, sorry, my bad. We know that potassium very strongly wants to be oxidized, and so it will want to stay in this state. It wants to stay as K+. We know from the electric potential, and we also know from the what we know about the reactivity series as well, that sodium is less reactive than potassium. It is less inclined to be oxidized, not by much. So it is more easily reduced. Now look, I know I'm basically I'm saying tomato here. I'm really talking about the same thing that's in the book, but the two ideas, really go with whatever you find easiest to understand. But as long as you understand that you're choosing the one that is most easily reduced in this case, or if you want to use the terminology of the book, it is the strongest oxidizing agent. Alright, so moving on down here, you'll probably figure out what happens next. So I'm going to do my potentials from the electrochemical series. Now, wandering up to chlorine, we find that it is plus 1.36 volts. Wandering to bromine, we find that it is 1.06 volts. Positive. Now, in the book, they would suggest to you which is the strongest reductant, and I have the same issue there, that I find that confusing, because they're not, you know, these substances do not particularly like to be reduced. They are crappy reductants. So you can go that way and go, okay, which is the strongest reductant? Basically, what's that saying? It's which of the two has the lower reduction potential, because strong reductants are at the bottom of the electrochemical series. So we can figure out that that's going to be bromide. The other way of doing it, or my preference, is to go, well, I know that chlorine is a strong oxidizing agent. The chloride ion wants to stay reduced. It will be harder to oxidize than bromine will, and so I know that bromine would be oxidized in preference. So either of those ways is the same, you know, it's basically describing the same thing, and they both work out pretty well. Now, there's quite possibly a shortcut to this that we'll have a look at later as well. But anyway, let's move on. Now, aqueous solutions are a trickier one, because we do have more than just two substances present, but we have water present which can be oxidized or reduced. So that just makes things that tiny little bit trickier, because you've got to think about your possibilities there. Now, zinc chloride, so we're going to have Zn2+. Now, we know that that would be being reduced to zinc, so it would be gaining 2 electrons and it would be forming zinc. That's absolutely terrible. Zinc, right. Now, we can also think about what happens with water. So water can be reduced, and I've just got to find the right reaction for that one. Now, actually, while I'm shuffling through the pages to do that, we know obviously that with the chlorine, Cl-, the reaction for that one that we were just looking at before on the electrochemical series is Cl getting 2 electrons gives us 2 Cl-, and that one had a potential, I've lost my page again. So the potential there for the reaction of chlorine was 1.36. I should really start to remember some of these things. 1.36 volts plus. The reaction of zinc is lurking down at minus 0.76. Okay, so when we then we've got to think about what's going on with water. So we have the reduction of water. Now this is the reduction of water, 2H2O and then we've got the oxidation of water, which is O2. Now remember, I'm writing the reduction potentials here, so this is a reduction reaction in the order that I'm writing it. So we've got two things going on here. So we've got the reduction reaction of zinc going on. Down here we've got the oxidation of chloride or of water being our other possibility. Now these are obviously the reduction reactions here. Now what we've got to think about again is which of these reactions is going to occur preferentially. So when we have a look at these ones here, remember for the reduction reaction we're looking for the stronger oxidant. Oxidants are higher up the electrochemical series, or thinking about it the way that I find fairly straightforward, although, and to be fair on the book and the clever people who wrote it, when you're looking at something like this, we don't really have things like the reactivity series to fall back on. So it's not obvious to me that this particular, the bottom reaction might be more or less favoured than the other one. The only thing that does tell us in this kind of case is the electrochemical series. So what we can see here is that this is a stronger oxidant, if you like, so it is more easily reduced than this substance here, which prefers to be reduced, if you like. Sorry, prefers to stay in an oxidized state. So it's not as easily reduced, it's not as good an oxidant. So what this means is that this one here is going to be preferable. Then when we go down here, what we can do is just think about the same things again. Which of these is a more stronger reducing agent, because reducing agents are oxidized. When we have a look at these, we can see that chlorine is a very bad reducing agent, it's a strong oxidizing agent, it's high up the electrochemical series. The one that we would use is this one here. So these are the two reactions that would occur for zinc chloride in water. We would find that the zinc would be reduced to zinc metal, and water would be oxidized to give us oxygen gas. I think that's right. Anyway, moving on. Now, I want to give you another example here. Now, this is an important example for a number of reasons. It's very similar to what I was trying to do on the board, and I have to apologize because I was having a bit of a brain fade there and trying to do something that wasn't quite going to work. So think about what we've got present. So we've got Na+. Now we know that wants, well, it doesn't want to, but it would be reduced to Na by gaining an electron. So this is reduction. And so things that are being reduced are acting as oxidizing agents, blah blah blah. We've talked about that before. So obviously the opposite thing that would happen is oxidation, and chlorine, well, we've got chlorine or chloride, which would be oxidized to chlorine. The reaction from the electrochemical series is from the reduction reaction. So we've look up our electric potentials again. I'm using the old textbook, so these might not tie up exactly with what's in the data book. So 1.36 for chlorine, minus 2.71 for sodium. Don't know why I wrote that. Okay, so volts on both of those. Now then we've again got to think about what the reduction reactions are. Now 2H2O plus 2E minus and we've got the so that's the reduction reaction. Now one thing that you might want to think a little bit about here when we're talking about why this is a reduction reaction and why or why one's an oxidation reaction, remember oxidation states. So when we're talking about the oxidation here, or the reduction, sorry, of water, maybe that's actually not quite the best way of describing it, because what we're actually talking about is the reduction of hydrogen. So the hydrogen goes from +1 to 0. Now, although it's not the same as the hydrogen reference electrode, which might be why that's maybe not the best way of thinking about that either. Okay, so but yes, you can see that there's reduction happening there, which is important. Now we've got the potential of that one. Now when we think about our other reaction that's going on, that is the O2. This is going to be annoying. There we go. O2 plus 4H plus 4E minus going to 2H2O, and this one has a potential of plus 1.23 volts. So as with the other one, it's pretty hard to figure out what's going on in terms of the which is the preferred oxidant and which is the preferred reductant, unless we think about the electrochemical series. So let's start off with reduction. Now we know that sodium doesn't really want to be reduced. It's not a good oxidizing agent because it's very reactive and it prefers to be oxidized. Sorry. So it is a stronger reducing agent because the value of the potential is very negative. When we have a look at the other possible reaction here, we find that this is a much stronger oxidizing agent because the potential is significantly higher. So the reaction that would be favored there, the reduction reaction that would be favored, is the reduction of water to produce hydrogen gas. Now when we go down here, similar sort of situation. We see that chlorine, when it's being oxidized, doesn't particularly want to act as a reducing agent. So it's the worse of the two as a reducing agent because it prefers to stay, it doesn't want to be oxidized. Now, and so what we're left with as the other reaction is this reaction here, the oxidation of water, which is going to produce that is going to produce, sorry, I'm having a mental blank here, so that's going to produce oxygen gas. Because we've got to remember that these are the reduction potentials that we're looking at. So this reaction that we're seeing here is the reduction reaction, but what's actually happening is oxidation. So the process that's happening at that electrode is the opposite way around. So same thing here, we would have had chloride, if that was the reaction that would have been favoured, changing to chlorine gas as it's oxidized. So in this case, water is being oxidized to form oxygen gas and H+. So the important reason I raised this example though is to think about what happens when we try to electrolyze a solution of sodium chloride. Do we produce any sodium or chlorine? We don't. But this is one of the significant ways in which we can produce sodium and chlorine. So that doesn't make a lot of sense, does it? The reason is, this is a really good example of non-standard conditions changing what happens. Because when we try, if we were to try and do this in a lab with sort of standard laboratory conditions of the concentration of sodium and chlorine and that kind of stuff, we would find that basically no chlorine was produced. But when this is done on an industrial scale, when the concentrations of things are much higher, so the amount of salt that's in solution is much higher, what actually happens is that the reaction of the reduction of the oxidation of chloride to chlorine is favoured, and so that is what happens. Now there are other processes as well that are similar to this that allow us to produce sodium too. So there are all sorts of variations, if you like, of non-standard conditions which will allow us to do things that we can't predict just from the electrochemical series. Okay, so another way of thinking about it is to, which you might have noticed already. Let's have a look back at our example here. So with the sodium chloride in water. Now, what we can do is we can take our equations, but we're going to write them in a slightly different order. I almost got it this time round, but that was actually a complete fluke. So we just need to think about the four reactions that are happening. So we know that we've got the reduction of the sodium ions. We know that we've got the oxidation of the chlorine ions, and we've got the reduction of water and the oxidation of water. So we can identify our four reactions. Now, all we need to do, or another way that we can think about this, hang on, I don't want that. Another way that we can think about this in order to figure out what's going on is, let's rewrite them, but we're going to rewrite them in the order of the electrochemical series. So we've got our two reactions here. We've got our two oxidation reactions up the top here. And we've got our two reduction reactions at the bottom here. Now, what you may have noticed, if we go back a page, is that the reactions that ended up being favoured based on the electrochemical series, when we look back here, are the two middle ones. So when we look at our oxidation reactions, so we're looking at the stronger reducing agent. So of these two reactions, it's the one that is lower in the electrochemical series. When we're looking at the reduction reactions, we're looking for the strongest oxidizing agent. It is the one that's higher in the electrochemical series. So the two that will be favoured, that will happen first, are the two that are in the middle. and this would have worked with our previous example of our sodium chloride and our potassium bromide. It's just that in these I actually had them written around the wrong way, so this would have been these two should have been at the bottom, and these two here should have been at the top, and then the middle two would have been bromide and sodium reacting. Same with these ones here, same with these ones here. So you might find this useful, but I would always recommend that you think about things in two ways in order to get your answer. If you write them in the order of the electrochemical series, the favoured reactions should be the middle pair. But you always want to be double checking and going, am I sure that this is an oxidation reaction and this is the the one with the lower reduction potential, so therefore the stronger reductant, and vice versa for the reduction reactions.